Hey everybody, so welcome to this second video about wave behavior. This one is going to focus on energy. So we have in the early 1900s some physicists doing work with electromagnetic radiation. Remember, that's the synonym for radiant energy. And a gentleman named Max Planck theorized that light energy, when I say light energy, I'm not just talking about visible light, but any of the forms of radiant energy, that radiant energy was not continuous, but instead was chunked or quantized is the scientific word we use. So in this analogy, if we think of moving from the floor here up to the second floor via a ramp, you can see that this guy doing that climbing could essentially be anywhere along that ramp. He could move up in an infinite number of tiny, tiny increments. But on this picture, you can only go from the bottom floor to the top floor via chunks or steps. So in other words, he could have the energy that corresponds to this step or to that one, but he can't hover in between them. So that's what Max Planck was proposing about energy that travels via waves. He said you can't have an endless limit of energy amounts. Instead, the energy must be in some little multiple of these tiny chunks. Einstein comes along and he sort of extends on Planck's thinking. So he says, granted, radiant energy acts like a wave. We know that we can measure wavelength and frequency of it. But he says that radiant energy, that's my kitty, radiant energy also acts like a stream of particles, which he called photons. Now make a note here. Photons are not really particles. Radiant energy, light, ultraviolet, X-ray, infrared, all those forms of radiant energy do not come in little physical pieces that could be massed. Instead, they are thought of as little chunks of energy, and we call those chunks photons. All right, so we have a mathematical relationship, and that mathematical relationship for calculating the energy of one of those little photons looks like this. So we're going to say that the energy of a photon has to be some multiple of this extremely tiny amount. Look at that, guys. 10 to the negative 34. So can you imagine taking this decimal place and scooting it 34 notches out here to the left and filling all those in with zeros? So that's it. That's extremely small. And any photon has an energy amount that is some multiple of that. And to figure out the energy of a photon, we're going to take that tiny amount and multiply it by the frequency of the radiant energy. Okay, let's do an example. What is the energy of a single photon of ultraviolet energy with frequency 2.38 times 10 to the 16 per second? Okay, that's our frequency, and we're asked what is the energy. Okay, now this one's pretty straightforward because our equation tells us that you can calculate the energy of a photon by taking Planck's constant, 6.626 times 10 to the negative 34, and that unit is the joule second. We take that constant and we multiply it by the frequency of this radiation we're interested in, 2.38 times 10 to the 16 per second. All right, before we grab our calculator, let's talk about units. This is a joule second, and this is a per second. So the second in the numerator and this per second, which is in a denominator, divide out. Okay, now we're going to multiply 6.626 times 10 to the negative 34. Multiply that Planck's constant by the frequency, 2.38, times 10 to the 16. And our answer is, I'm going to use 3 sig digs for my answer, 1.58 times 10 to the negative 17. That was 1.58 times 10 to the negative 17 joules. Okay, look at this number, guys. 10 to the negative 17, that's extremely small. But that makes sense because this equation allows me to calculate the energy of a photon, one photon. Okay, so that's our energy for this ultraviolet radiation. Let's look at a second example. What's the energy of a single photon of orange light with wavelength? Wavelength 692 nanometers, and we're trying to find energy. Okay, energy is equal to Planck's constant times frequency, and I was not given frequency. But I was given wavelength, and on the earlier video, we said that wavelength times frequency is a constant, the speed of light. So if I know the wavelength and I want to find frequency, I've got frequency equals speed of light divided by wavelength, 3.00 times 10 to the 8 meter per second. That's my speed of light. And my wavelength is 692 nanometers. Okay, checking the units. Meters and nanometers are both length units, but they don't cancel. So I have to take advantage of my nanometer-meter equivalence, which is 10 to the 9 nanometers. That's a billion nanometers in a meter. So that's going to cross out the nanometers and to cross out the meters. And now I have 3.00 times 10 to the 8 times 10 to the 9. That's my numerator. And I divide by, put my denominator in parentheses, 692 times 1. And I have, for my frequency, 4.34 times 10 to the 14. Don't forget to check out here to the far right of your display. And all of my units have canceled except the per second, which is the correct unit for frequency. All right, now once I have found the frequency of my orange light, now I can use my second equation to get the energy of a photon of orange light. That's equal to Planck's constant times frequency, or 6.626 times 10 to the negative 34 joule seconds times, and here is my frequency, 4.34 times 10 to the 14 per second. Again, this second, which is in the numerator, cancels out this per second, which is in a denominator. And when I multiply these two pieces together, Planck's constant times the frequency, I get 2.87. Oops, I'm going to round that up. 3 sig digs, 2.88 times 10 to the negative 19, and my unit is joule. Once again, a really tiny number. So this is the energy for orange light. All right, let's take a minute and compare the two. In our first problem, we found the energy for ultraviolet radiation. And in the second one, we found energy for orange light. Which of those two numbers is larger? Which one of these is higher energy, even though they're both extremely small? I hope you can see that the energy for ultraviolet is a higher number than the energy for orange light. 10 to the minus 17 is a bigger number than 10 to the minus 19. So the ultraviolet energy is higher than the orange light energy. And now let's compare the frequencies of the two. This was the frequency of the orange light, and this was the frequency of the ultraviolet. Which of those is bigger? And I hope you can see that the frequency for the ultraviolet was also bigger than the frequency of the orange light. So that tells us that energy and frequency have a direct relationship. As frequency gets larger, energy will get larger. So lastly, you remember on our last video, we talked about this inverse relationship between wavelength and frequency. Well, now we're going to add to that. So we have when wavelength is long, frequency is low, and energy is also low. And when wavelength is short, frequency is high, and energy is high. Okay, take a minute and digest that. So these relationships are important for you to understand. This equation for calculating the energy of a tiny photon and its dependence on frequency is important also. All right, guys, I hope that was helpful.